This lecture is about subtyping. Subtyping is a particularly important in the design of object-oriented languages, where we have the relation between superclasses and subclasses, and this relation is basically subtyping relation. So the first notion that we have to learn is principle of subtyping. So this principle of subtyping states when a type A is a subtype of another type B. So we are going to write A subtype B using this notation. So this symbol stands for is a subtype of, is a subtype relation. So the principle of subtyping, so notice that we refer to this one as principle that is applicable to every pair of types. So this principle of subtyping says that A is a subtype of another type B if we use an expression of type A whenever or wherever expression of type B is expected. So what this means is that suppose that we have a program and we have some context here. And in this context, we are currently expecting an expression of type B. So for instance, we might be calling a function f which takes an argument of type B. So we have a context where an expression of type B is currently expected. Now, A is a subtype of B if we can use instead an expression of type A whenever or wherever an expression of type B is expected. If we can use this expression of type A in all such contexts, we say that A is a subtype of B. That's the principle of subtyping. And so this is the notation for writing A is a subtype of B. A is a subtype of B, or B is a supertype of A. So these two statements are equivalent. So again, let me repeat the principle of subtyping. This principle of subtyping says A is a subtype of B. A is a subtype of B if we can use the expression of a type A wherever expression of type B is expected. That's the principle of subtyping. So with this principle of subtyping in mind, we can actually start to develop subtyping rules. Let's first consider two structural subtyping rules. Subtyping rules. So the first is reflexivity rule, which says A is a subtype of A itself. This is reflexivity rule. And the second is transitivity rule. A is a subtype of C if A is a subtype of B and B is a subtype of C. This is transitivity rule. But this makes sense according to this principle of subtyping. So you should be able to explain all these subtyping rules according to this principle of subtyping, because it is a principle. So this rule makes sense because when you are expecting an expression of type A, you can definitely provide an expression of type A. So this makes sense. So in this way, we can justify this reflexivity rule for subtyping. What about this one? Transitivity rule. This subtyping relation says that whenever you are expecting expression of type C, you may instead provide expression of type B. And this one says whenever you are expecting an expression of type B, whenever you are expecting an expression of type B, you may instead use expression of type A. Then by transitivity, we can say that whenever you are expecting an expression of type C, you may instead use expression of type A. So by transitivity, we may conclude this subtyping relation. These are the first two structural subtyping rules that we can justify with this principle of subtyping. Before we proceed to developing the remaining subtyping rules, I'd like to talk about the semantics of subtyping. So this is the syntax for writing subtyping relations. And the question now is, what's the meaning of these subtyping relations? Semantics of subtyping. So the question is, what's the meaning of this subtyping relation? So there are two approaches. The first is subset semantics, and the second is coercion semantics. Coercion semantics. So the subset semantics says A is a subtype of B if the set of values of type A. So this is the set of values of type A. So we have V1 of type A, V2 of type A, and so on. So we collect all these values of type A, and we collect all the values of type B as well. So this is the set of values of type B. If we have this subset relation between this set and this set, then we say that we have this subtyping relation. That's the subset semantics. So here's an example. Suppose that for basic types we have nat for natural numbers and int for integers and float for floating point numbers. And let's assume that both nat and int use a 32-bit word to represent natural numbers and integers. And furthermore, assume that this nat and int use precisely the same format in this 32-bit word. Then we can say that we have this nat is a subtype of int according to this subset semantics, because literally the set of natural numbers, say 0, 1, 2, and so on, is a subset of the set of integers, -1, 0, 1, 2, 3, -2, etc. So literally the set of natural numbers is a subset of the set of integers. So we have this subset relation. And according to this subset semantics, then we can say that that is a subset, that is a subtype of int. That's this subset semantics. And the other way of interpreting subtyping relations is to use coercion semantics. In this case, A is a subtype of B if you can find a unique coercion function. Coercion function from A to B. And what this coercion function does is to convert the value of type A to another value of type B. So here's an example. Let's compare int and float. Suppose that we use a 64-bit word to represent the floating point numbers. Then we can definitely say int is not a float, because int is literally 32-bit word, whereas this float or floating point numbers uses 64-bit. So the two formats are just incompatible. So we cannot say that int is a particular case of a float. But suppose that the compiler provides automatic conversion from int to float whenever necessary. For example, let's just say we are trying to add integer 1 with the floating point number 2.0. So strictly speaking, these two values are incompatible because this one is stored in 32-bit word and this one is stored in 64-bit word. But suppose that compiler automatically inserts a coercion function from int to float. So it automatically inserts a coercion function, something like f. And this coercion function automatically converts this one into the corresponding floating point number 1.0. So if the compiler or the language system takes care of this coercion, automatic conversion, then we say that int is a subtype of a float because you can use integers just like a floating point numbers thanks to the compiler that automatically inserts this coercion function. So we learned that there are two different ways of interpreting subtyping relation, subset semantics and coercion semantics. And in this lecture, we are going to discuss only, we are going to assume subset semantics. Now let's develop subtyping relations. So the questions that we'd like to answer are: what kind of subtyping relations can we derive from this from the principle of subtyping? So principle of subtyping, we already have two subtyping rules. The first is reflexivity rule. This is a reflexivity rule. And the second is a transitivity rule. A is a subtype of C if A is a subtype of B, and B is a subtype of C. This is transitivity rule. Now, assuming that this set of types, so we have base types and this product type and sum type, and we also have function type, and we have this reference type. And for base types, let's assume there are two base types, net and int, where we assume net is a subtype of int. And the questions that we'd like to answer are: what kind of subtyping relation do we have for instance, product types? For example, when do we deduce A product of B is a subtype of A prime product of B prime? And what about the sum type? And what about function type? And what about reference type? That is, reference A is a subtype of reference B. So these are the questions that we'd like to answer. So before we proceed, let's introduce another typing rule that allows us to use subtyping in typing judgment. And the rule is called the subsumption rule, which says, suppose that you have this typing judgment. We know that expression E has a type A. And we also know that expression A is a subtype of B. Then we can deduce expression E has type B as well. And this rule is called subsumption, subsumption. So if we have this additional typing rule, this is a typing rule because it deals with these typing judgments. If we have this subjunction typing rule, then we can actively use this subtyping relation in typing judgment. So for example, we can, if A is net and B is int, by applying this subjunction rule, we can convert an expression of type A to an expression of type int. So we can convert net to int. Then how can we justify this subjunction typing rule? Again, we can go back to this principle of subtyping to justify this subjunction typing rule. This principle of subtyping says A is a subtype of B if you can use expression of type A whenever an expression of type B is expected. So here, we are expecting an expression of type B. So you have to provide an expression of type B here. But the interpretation of this subtyping relation says you can instead provide an expression of type A. So you have an expression of type A here. So here, we are expected to provide an expression of type B, but thanks to this subtyping relation, we may instead provide the expression of type A. So again, we just go back to this principle of subtyping to justify this subjunction rule. Now, let's go back to these subtyping relations. What kind of subtyping relations can we derive? Again, from this principle of subtyping. So the first case is product type. So let's first talk about product type, and then sum type, and then function type, and finally this reference type. So the question is, the first is the product type. The question is, suppose that we have this subtyping relation between two product types, or we'd like to deduce this subtyping relation. And the question is, what is the premise? What should we verify in the premise of this subtyping rule? So let's consider an example. Suppose that you have net times net. You have a pair of natural numbers, 0 and 0. And 0 is an integer as well, and this is also integer as well. So perhaps you can deduce this is also int product int. And that's precisely what this product, the subtyping relation for product type states. So in order to deduce this one, you have to show that A is a subtype of A prime and B is a subtype of B prime. So that's the subtyping relation for product types. You just compare the two components pairwise in the same position. You compare A against A prime and B against B prime. And similarly, we can easily show that for some types, some type B is a subtype of A, some type B, A prime, some type B prime, if A is a subtype of A prime and also B is a subtype of B prime. And this makes sense because you always compare the two type components in the same position, the left one against this left one, this right one against this right one. When you analyze this right component, it doesn't matter what kind of type you have on the left side. So therefore, we have these two subtyping relations in the premise. Next, let's discuss function type. In the case of function types, we have to think about the relation, the subtype relation more carefully. So it requires a bit of thinking. So the question is, what is the premise for this subtyping relation? So to figure out the premise here, let's consider an example first. The first example is, let's say we have function f of type a arrow net, and let's say we have function of z of type a arrow int. Now, of course, we assume that net is subtype of int. The question is f subtype of g or the other way? So which is the case? So it turns out that we have this relation. F is a subtype of G. So let's see why. Again, you have to use this principle of subtyping to figure out why this subtyping can be justified. So if this is the case, so F is indeed a subtype of, A net arrow net is so we'd like to show that A arrow net is indeed subtype of A arrow int. And according to the principle of subtyping, this subtyping relation says that whenever or wherever you are expecting a function of type A arrow int, so you are expecting a function of type A arrow int, you may instead provide a function of type A arrow net. So let's start with the assumption. We are expecting a function of type A arrow int. So for instance, we are applying this function to an expression of type A. So expression E has a type A. And if we have this function f, then the whole expression, the application f applied to E is going to have a type int. Now, if you can manage to use a function of type A arrow net here, then you can justify this relation. So let's just see what happens when you instead use function g of type A arrow net in this position. So we have g applied to expression E. Expression E has a type A, so this one, expression E has a type A, and G has a type A arrow net. Then, by the typing rule for function application, we have a type net. So G applied to expression E has a type net. But we can apply this subsumption rule. So, because net is a subtype of int, we can deduce G applied to expression E has int type as well. So everything is fine. So you wanted to provide an expression, a function of type A arrow int, so that you can produce an integer. The final goal is to produce an integer here. So instead you provide function g of type A arrow net, but in the end, you show that this function application has a type int that we wanted to produce here. So this example illustrates that when you are expecting a function of type A arrow int, it's fine to provide instead another expression of type A arrow net. So when you are expecting A arrow int, you instead provide A arrow net. That's okay. So we have this subtyping relation. But because we have this subtyping relation, net is a subtype of int, we can generalize this finding to obtain this rule. A is a subtype of B. A arrow B is a subtype of A prime arrow B prime. But in this particular case, the argument type is the same. So let's use the same argument type. So this is A. If you can show that B is a subtype of B prime, then you can deduce A arrow B is subtype of A arrow B prime. So formally, we say that this function type arrow is covariant in the position of return types. Covariant means that varying in the same direction. So in the conclusion, the argument types are the same, but the return types are different. If we move from the left side to the right side, we see B and B prime. And the direction is not reversed. We use the same direction. If we read left to right, we see B and B prime. So the direction is the same, B, B prime, B, B prime. So in that sense, we say that these function types are covariant in the return types. But this is the rule that you want to remember. That's the first part of the subtyping relation for function types. And the other case is this one. This time, the return types are the same, but the argument types are different. Let's say we have A arrow B, the subtype of A prime arrow B. And the question now is, what is the subtyping relation between A and A prime? So that's the question. So this is the first part in the subtyping relation for function types. And this is the second part. What is the premise? And this time, let's consider as an example, let's consider a function f of type net arrow b and another function g of type int arrow b. And perhaps to your surprise, we do not have this subtyping relation. This is not the case. Instead, int arrow b is going to be subtype of net arrow b. So let's see why this is the case. If int arrow b is subtype of net arrow b, then according to the principle of subtyping, you can substitute an expression of this type wherever an expression of type net arrow b is expected. So let's say this context expects an expression of type net arrow b. So perhaps we are applying this function to an expression of type net. Then the whole result will be this application is going to have a type b. So that's the context. Now let's try to use instead function f of type int arrow b. So can we instead of this net arrow b, can we instead use a function f of type, say, net arrow b here, int arrow b. So originally we wanted to use this net arrow b, but instead we'd like to use this function f of int arrow b. And the question is, can we type check this function application and show that it has a type b? So let's see. So we have a function f. We have a function f of type int arrow b, and it has a type net. But this time, let's apply the subsumption rule to this expression e. We have a net is a subtype of int, so we can deduce that expression e has type int as well. This is by applying the rule subsumption rule. Now, fi has a type int arrow b, and the argument e has type int, so f applied to e has a type b, so everything is fine. So it turns out that int arrow b is a subtype of net arrow b, not the other way around. And let's generalize this finding. The finding is this one. Here, the return types are the same. We use the same return type b, here. And the argument types are different. But this time, the type that is subtype of the other type appears on the right side. So you can generalize this, find this example, and show that A prime is a subtype of A. So this time, we see precisely the opposite of what we saw here. In the first case, we have covariant, a phenomenon called covariance, that is, these return types preserve the same direction, B, B prime, B, B prime. But this time, the argument types are reversed. We have A, A prime, but here you have A prime, A. So the direction is different. If you draw arrows from A to A prime, their directions are reversed. Their directions are opposite. So in this sense, we say that function types are contravariant in the argument types. That means that the subtyping on function types is contravariant. That means that the direction is reversed when you consider the subtyping between the argument types. You have A prime, but in the premise you have to show that A prime is the subtype A. So we say that function types are covariant in the return types, but contravariant in argument types. Now let's combine these two subtyping relations and then derive the subtyping rule for function type. A arrow b is a subtype of A prime arrow b prime. The function types are covariant in the return types, so b must be subtype of b prime, but it's a contravariant in the position of argument type. So now A prime is a subtype of A. So this is the subtyping relations for function types. Now we have one case remaining. So we have considered this product type and subtype and this function type, and the remaining case is this reference type. So let's see this remaining case. So the question is, suppose that we have this subtyping relation. Reference A is a subtype of reference type B. And the question is, what kind of premise should we provide to deduce this subtyping relation? Again, we want to go back to the principle of subtyping. According to the principle of subtyping, this subtyping relation says wherever you are expecting an expression of types reference B, you should be able to instead use an expression of ref A, type ref A. So what kind of context do we have where we are expecting an expression of type ref B? There are two cases. The first is we are dereferencing this reference. So for instance, if this is expression E, we are dereferencing it. So that's the first case. And the second case is we are assigning a new value to this reference. So we are updating the content of this reference. So we have two kinds of context where we are expecting an expression of type ref B, this one and this one. And in order to have this subtyping relation, we should be able to instead supply another expression of type ref A. So here, instead of expression E, we should be able to provide another expression E prime of type ref A. And here, instead of expression E, we should be able to supply another expression E prime of type ref A. And let's see what kind of relations we can derive between this type A and this type B from these two cases. So the first case is this bang operation, dereferencing. So we have bang of something. So here we are expecting an expression of type ref B, but instead we provide an expression of type ref A. And what is the expectation here? Because we are currently expecting a reference of type ref B, the whole expression is going to have type B. Now what happens if you supply instead an expression of type ref A? This one has a type A because you are dereferencing a reference of type ref A. So this bang E is going to have type A. But we will have to provide an expression of type B. So therefore, you have to have this subtyping relation. Otherwise, you will not be able to we will not be able to use expression E of type ref A. So from the first scenario here, we deduce that A must be subtype of B. What about the second context? The second scenario. In the second scenario, you are expecting an expression of type ref B. So here, perhaps you have a value of type B. But in order to have this subtyping relation, it should be fine to use instead an expression of type ref A. So here we use an expression of type ref A. So by evaluating this expression E, you are going to create a reference that is pointing to a heap cell that contains some value of type A. But you'd like to update this content. You'd like to update this heap cell with a value of type B. So in other words, you are going to store this value V when you are actually expecting a value of type A. So you are expecting a value of type A, but you are providing a value of type B. So what that means is that you should be able to convert this value of type B to type A. So we see precisely the opposite of what is happening in the first case. So combining these two cases, we obtain the subtyping rule for reference. Reference A is a subtype of reference B if A is a subtype of B and also B is a subtype of A. So these two conditions do not necessarily imply that A is completely equal to B. That may not be the case in the presence of complex subtyping relations in object-oriented languages. They are almost equivalent, but they may not be the same. So to summarize, in order to show that reference A is a subtype of reference B, then you have to show that A is a subtype of B, and at the same time, B is a subtype of A. So in this sense, we say that the reference types are non-variant. It's neither covariant nor contravariant. It's a non-variant. You have to show that these two subtyping relations hold. So as an application, let's look at the subtyping relation in the Java language. In the Java language, we have this array type, array A. So we can think of this array type as a small variant of this reference type. Because, for example, you can dereference this array to obtain a value of type A, and you can actually update the element of this array with another value of type A. That's what we can do with this reference type. With the reference type, you can actually dereference it with this bang operation to obtain value of type A, and you can also update this reference with another fresh value of type A. So essentially, this array is just a collection of references. So in this regard, we can almost equate these two types. So that means that the right way of formulating this subtyping relation between these two array types is sorry about this. So the right way to formulating the subtyping relation between two array types is you have to show that A is a subtype of B, and also B is a subtype of A. If we recall the fact that arrays are almost the reference types, except that it just contains many heap cells. So this is the right way of formulating the subtyping relation between array types. But it turns out that in the case of Java language, one of the subtyping relations in the premise is missing. In the case of Java language, we have this subtyping relation. A is a subtype of B. And this condition is missing. This is missing. This is the subtyping rule for array types in Java. So what that means is that, let's go back to this example. When we are trying to develop the subtyping relation for these reference types, we consider the two scenarios. First, the dereference, and the second, update. And this one, B is a subtype of A, was obtained from analyzing the second case, this update. The first one, this one came from this dereference, and this one came from this update. But in the case of a Java language for array types, this one is present, but this one is not present. And from the previous example, this one comes from update. So what that means is that when you are updating an array, so you have an array of type A, and you are updating some elements of this array with a new element, new values of type A or something else. But the Java language omits the second subtyping rule, second subtyping in its subtyping relation. So that means that this is not verified at compile time. So that's the reason that every time you update some element of an array in the Java language, you have to perform this check at runtime. So in other words, there is always a runtime overhead in array updates. You have to basically pay the price at runtime because you didn't check this relation at compile time. If Java language had the second premise here in its subtype relation, then this overhead, the runtime overhead, would be eliminated. But that is not the case in the design of Java language. So it's controversial whether the omission of this second subtyping relation is a feature or bug in the design. You have to pay the price at runtime with this dynamic tag check. So remember that every time you update an array in the Java language, you have to pay the price with a small overhead, runtime check overhead, because the second subtyping relation is missing.